OMFIT because it has a lot of cool new features. I'm going to load that and then type OMFIT, and then a nice little trick. If you know the module that you want to load, you can do -m, OMFIT profiles. And then you don't have to do file import module, which is a lot of clicking. So these are getting more advanced each week. I feel like I can do that.
Yeah.
All right, so it takes on average about 9 to 10 seconds to boot this thing up. And then it's going to import the module for us. And so here we are in the typical OMFIT interface. And we have the module here with the usual scripts, plots, and so on. So if we double click on it, we get the GUI, which asks us for a device. We'll use G3D. Shot number, we'll use reference shot because it has a lot going on, and we use it for our regression tests, 161409. And then we'll use a 2-second window from about 1 second to 3. And we can use Python commands in here, so we can say from 1,000 milliseconds to 3,000 milliseconds and 1 because it's not inclusive. And we'll do 200 milliseconds, which gives about 10 slices. Okay, so there's some really cool new features that are called out here for 2D fitting, but we're gonna start with 1D fitting, which has been the standard for many years. So switch our workflow here, and then instead of doing it all at once, we'll go through manually and do each step along the way. So the first step is to fetch the raw data from MDS Plus, where it's stored, and we're going to need an equilibrium to use to map the R and Z position of each measurement to flux surfaces. And then we have some options for particular diagnostics. There's different levels of CER analysis, for instance, on D3D. And so this part is really where the machine dependence of this module comes in. After this, we strive to make all the operations as general as possible. So we have some optional diagnostics and a filter scope choice for different ELMS. We can check which one we want to fetch by, for instance, plotting it, which brings up a plot like so. And so this filter scope does indeed see some ELMS, which are identified. And so we'll go ahead and stick with it.
Maybe one thing to say is that we assign a phase during, that is negative during the ELM, which goes from -1 to 0 during the ELM and 0 to 1 between two ELMs. And so we're gonna, that's how.
You can see the ELMs are identified in red here, and then the phase is negative during the ELM, positive going from 0 to 1 to the next ELM, and we can use this then to filter our data based off of the ELM phase. Okay, so basically we need to just fetch a whole bunch of data. So I'm going to click this and let it go. So it's going in parallel and fetching the data from each of these diagnostics. And it's actually doing more than that. It's going to run a couple different scripts. Whenever you click a button in OMFIT, it's basically running scripts. And here they're nice and ordered for us. So it's going to run this fetch script, which will get the data. It's going to assign some timing information to each of these data points. It's going to form some dictionary of the available channels so that we can toggle them on and off. And then finally, most importantly, it's going to map them from R and Z to flux surfaces. And so it's going to tell us that it's doing each of these steps as it goes. It's assigning timings, initializing channels, and then mapping rho, psi, etc. So that's now every single data point at its native time base knows its position in rho and psi n, for instance. And so what has this done? It's formed some outputs. One of them is the raw data for each diagnostic here. Each diagnostic has subsystems. Each subsystem has channels. And this channel has measurements, as well as now some ELM information, as well as the mapping to the equilibrium state. And each of these can have a different number of times. So you see this one has 194 times, and the next channel has 300 plus times. So this is the fundamental problem. We need to get all of this information onto one time base, namely the times at which we want the profiles. Okay, so then as we move along, we can select different channels. And I'm going to jump over to the CER vertical channels and look at a subsystem. One thing I didn't mention is that we chose to split up the CER during the fetch stage by the beams. And it's just a checkbox. So different beams, the left and right sources, have been split up into different effective diagnostics. So if I choose one, I see it has channels that I can toggle off or on. And also, I can just toggle the whole system on for different measurements. And the colloidal velocity has been deselected by default. I'm going to select it now. So this is actually a tricky one in D3D because it involves some complicated corrections in the core where the rotation is going rather fast. And so there are some options. We can use the true data that's measured there, but perhaps the analysis is not quite correct, or we can ignore it. I'll ignore the data in the core based off of a temperature threshold. So I'm going to go through and turn on the colloidal velocity measurement for each of these beams here.
And this is important because without the colloidal velocity, you cannot calculate the radial electric field. So
That's right.
One thing that we want to show, I guess, towards the end of the tutorial is how after fitting all of these profiles, you can also get some derived quantities, and the radial electric field is a neat one that OMFIT profiles can calculate.
Exactly. Okay. So we can also check the data with the raw time series. So this is just the raw data plotted in time for many channels. And you can see, which channels have consistent data, which don't. You can sometimes immediately identify problematic channels using this plot. But we're going to move on for speed to the slice stage. This stage is basically where we want to take all those different time bases and get the data onto the times of interest. And we're going to do that by convolving them with some sort of window function, the simplest being a boxcar, but a more advanced one perhaps being a Hanning function, which will weight points nearer the time of interest more than points further away. Within an averaging window, we might take 20, we might take, 50. Our points are 200 apart. So there's different options for how the error will be propagated through this convolution process. And if you need more information, there's often question marks here that'll tell you all about it. And so you can see that it explains each of the options that are in this dropdown here, similarly to the Hanning window and other window functions defined here. Okay. One option is to interpolate data where it's missing. This is if you have a time averaging window that's smaller than the gap between data points, you'll get no data there. If you want data, you could linearly interpolate between the points on either side of your window. This is a very powerful option, but a dangerous option as well. Be aware of large gaps in data that result in unrealistic interpolations. Another one is a causal window, which is more physically safe to do, I think. So we'll choose that one. And then finally, there's ELM selection. So we chose a filter scope and identified ELMS using that filter scope. And so now is the point where we could select phases in which we'll say data is good, and we'll take it into account when we do our convolution to the time of interest, and anything outside of this phase will be ignored. And so from saying 0 to 1, we're saying we're ignoring the times during the ELM burst where the phase was -1 to 0. And we're doing this based off of knowledge that these ELM bursts can scatter the data mostly in the pedestal, and we want to avoid the scattered data messing with our convolution to the time of interest. We can also accept an ELM-free phase so that if there's a long period with no ELMs, this phase is correctly accounted for. Again, we could plot it. It would be the same plot as I showed before. So I'm going to hit this button here to slice all the data. And it's going to go through each of these raw diagnostics, subsystems, and channels and convolve it to the times that we've selected up here. All right, so it's going to do that in parallel. And again, it's running scripts here, namely this slice one. And you can see the script that it's running up top.
Nick or Orso, was one of you going to address the spatial averaging option there at the top?
No.
I did not plan on using it, but it is an option that will be detailed in the documentation. There's a question mark here to give you all the information you need.
Right, so that option is used when, for example, there is a plasma sweep, for example, and we want to average multiple, it's a.
You have jogs.
Yeah, exactly. If you have a jog of the plasma, you can use that jog and superimpose the data that comes from different time slices during that jog. But it's I think quite advanced of a feature, but it's there.
Okay,
Really
yeah.
useful. Probably very useful.
Right. I think it used to be very useful, especially in the past when the diagnostics. Right, but so when the diagnostic didn't have a very high spatial resolution, people used to do jogs a lot, jogs of the plasma a lot, and instead now, for example, the Thomson scattering resolution, the Pedestal is very high, so there's actually no much need for that. But if you have a diagnostic which has a coarse spatial resolution, and you have these sweeps in the plasma, then that's something useful.
Isn't it still done for CER to get a very precise ER measure?
For example, yeah. If you have, it's also something that makes sense only for certain shots and during certain times when there are these sweeps, right? Because when you do that, you want a stationary plasma, and you want kind of a smooth.
Does this option let you overcome the problem with slicing, where you could? Or
yes.
Okay.
Yeah. All right, so it's always a good idea to pay attention to things that are printed out in the console when you click buttons. They're there for a reason. So it went through and sliced each diagnostic. It then formed some quantities based on the equilibrium at these specific times that take a little bit more to calculate. So trying to be efficient there. And then it tells us that there's a minimum time to capture each channel from each diagnostic at each of our requested times. And our window is well above that time, so this is green, which is happy. It would be red if it was not. Okay, so then it's also good to be aware of what's happening in the OMFIT tree when you push buttons. Basically, we've added a new output called slice. This is each diagnostic, which is now a nice square array for each value in it, channel by time. So here's the Thomson density in an array of channel by time. If you remember the raw data, each channel had a different time base, and so we couldn't form it in such a nice matrix. Of course, our ultimate goal is to have this be row by time. Okay, that's what happened here. We can go back to the selects now, and if we replot a time series, oh, I don't know if I actually plotted the time series before. I did the time series. So before, where it was just the points, you can see now it has the points and bar, which shows the sliced data. So this is where we've convolved to each of the time points that we want. And you can see it goes through the points rather well, which is encouraging. There are some gaps where points were missed. Okay. And we can also look at the sliced data in profile form before we even bother fitting. And this is useful because you might see a random channel that you might not like, and you can click on it, and the vertical V07 channel for the CER looks a little suspect here. And so we could go in and turn that one off if we wanted to. 30 left. Let's do it. 3 left. 7.
Yeah.
Turn it off. Right. Okay. And we would do that more carefully for each of the diagnostics if this was the first time we're going through a shot. But for now, in the interest of time, we're going to move on to the next step, which is fitting it. So here you have your choice of coordinate, row, or psi-n, your fitting range, and the resolution on which you're going to output your fit grid. So, you know, this will be about 120 something points in row, or 240 actually. Okay, so now you have each measurement, and you can fit them as you go. I'll just skip to TE since it's a nice profile with the pedestal, which is often a problem when fitting or a challenge. And you can see that you have an option to transform the data. If you click the question mark, you'll see that it performs this transformation of the data before fitting, fits in that space, and then back transforms it back. And so why would we do this? We would do a log transform to ensure that the result is going to be positive when we back transform it. Okay, so this takes into a long-standing problem and solves it instead of making sure that your splines don't dip below 0 in the edge of a density or temperature fit. You also have a symmetry option, which if we click the question mark, includes core points symmetrized across row equals 0. So it takes the core points and just flips them across core 0 and fits from -0.2 to 1.2. And this is useful if the fitting method that you're using doesn't have an explicit option to force the derivative to be identically 0 on the core, because this will essentially do that due to symmetry. Okay, and indeed that's the case for the radial basis functions.
So is that treated as a function of flux or something across the core, or really radius? Because it isn't symmetric in radius.
No, in row. It's going to flip it in row. It's going to include all the points between 0 and 0.2 row, mirrored between -0.2 row,
in row,
and 0.
not in major R.
That's correct. Yeah. Okay. So here's a default fit, so we can click fit, and it'll also pop up a plot. So we just fit these 10 time slices. The default plots, this 1D one, these plots are interactive, so if we use the arrow keys, we can progress through time, see how our fit did. It looks pretty good. You can see it's capturing the pedestal well. and it has a flat core, and it does have some wiggles here mid-radius, which, you know, depending on who you talk to, this is desirable or not. And so
It shouldn't be whether it's desirable, it's whether it's real.
yeah, well, it depends. For instance, if your fit had a negative gradient and you're doing a transport code that doesn't like negative gradients, you might use a different fit method if it was marginal, etc. So to demonstrate that, we can save this fit. We can say we like it. We can say this is our RBF fit. It looks pretty good, but I don't know, maybe I want to try a more traditional fit. So maybe something like this polynomial core and exponential blend in the edge. This is a very long name for basically a modified tanh with a polynomial core instead of a linear core. Okay. So this is developed by Brian Gerson. Has a number of options to get it to do really beautiful fits. And so we could redo this. And you can see now that this one actually doesn't propagate the errors, but you can see it has this nice modified tanh representation of the pedestal and a really smooth core because we used just the second order polynomial in the core. This would basically guarantee that you're not going to get too much going on in your transport code in the core here. And then, you know, these look both good, so maybe I want to compare them. I can do that. Well, let's see how good this was. So I can plot the residuals and the chi-squared. So this is a time series of the chi-squared for this fit. You can see that one of the points maybe was worse than the others. And so we can, oops, I lost my other plot. Put that plot. What is the second to last time? Let's see if we can find it. So it looks like this one struggled a little bit more than the others. We could go and maybe tweak the polynomial number, give it a lot more just for fun, and we can refit just this one time. 800. And so now if we fit, it'll only fit this one time, and it doesn't look like it changed it very much. But that's an option that we have to go through and edit individual time slices. If we then want to compare to the RBF, which we had saved previously, we have the option to do that. And you can see that the fits are basically right on top of each other. So that's promising. The two.
This is for this time slice.
Yeah, because I still have the time selected in the fit times here. You know, if I wanted to compare more. I could. So here, the RBF reduced chi-squared is not really meaningful because it's a 2D fit instead of a 1D fit. But we can see here this plot is interactive, and so we can progress through time and see how the two fits differ. You can definitely see that the current fit is generally smoother than the RBF. The RBF has more dynamic structure in the core. And these were options that we chose. I mean, we chose the second order polynomial to accentuate that. So we could make these two methods look more like each other if we wanted to. Okay, that's basically what I wanted to go through, other than the fact that I forgot to say that when I use the modify tanh options or some functional form option, that's based off of what the data actually looks like. And so I usually actually turn off this transform because you want to fit a function that looks like this data, not that looks like the log of this data. So I would typically do that, but I forgot to here. So I'm going to revert this back to radial basis functions, and then just fit everything so that we have it. So I'm just going to go with the defaults for all of the options. You actually notice that most of them have the radial basis functions as defaults because they're quite fast and robust. An exception is the poloidal velocity, which has a constrained spline because we need it to be 0 in the core. And so you can put constraints into these splines that allow for that. I might bump up maybe a couple more not locations. Okay. So fit all. So this will go through and fit them all as we go. I'll just say that we've formed a few new outputs. We have the fit. So we've done TE so far. And you can see now it's a matrix of time by row, whereas before we had channel by time, right? So that's basically success. Our ultimate goal was to get a measurement in a time by row grid. We also have the fit history, which is where it stored information about the RBF fit so that we could compare it to the other fit, for instance. Okay, so it's going through and populating all of these. Here's our stored fit from previously, and now we have all of these. You'll notice that the poloidal velocity also includes the derivative of itself, and that's because we use this spline, which uses a Monte Carlo method for uncertainty quantification. Because it's doing a Monte Carlo and it has an analytic derivative, we can also get the Monte Carlo solution of the derivative and its uncertainty. And so we store that directly rather than calculating it numerically later on. So if I plotted this, you could see the fit as well as its derivative. A similar upgrade is coming to the RBF hopefully soon. But many of the methods, such as Gaussian processes, also return derivatives with proper uncertainties on them. Okay, so now that we've done that, this is essentially the main product of this module, which can be fed into other transport codes or any MHD code or anything that you need. However, sometimes these codes need more than just the raw measurements. Things like omega E might be needed. And so there's something called derived quantities that we can then calculate based off of these fundamental quantities. So I'll click on that. And it's going to go through and calculate a series of derived quantities, tell me if they were successful or not, and populate one final output called derived with many quantities in it, such as it's formed the density and the rotation together to give us an angular momentum. It's analytically calculated the computationally calculated the derivative for anything that we didn't have the analytic derivative for, and it's calculated ER based off of various components, for example. Okay. So there were some options that we could have done because this data set can get quite large here. So you can toggle things on and off. And then we also have ways of adjusting our fits to align the separatrix. So one of the problems commonly is that we know that the edge of the plasma is where the temperature pedestal, the foot of the pedestal is, but EFIT told us that the edge of the plasma was somewhere else in R and Z space. And so we have an inherent discrepancy between two measurements. And we might have a physical reason too. Maybe there was a 3D field turned on, and so the 2D representation of our flux surfaces might have a centimeter shift based off of different toroidal locations, right? Plasma is slightly closer to the Thomson, where it's toroidally located, and maybe slightly further from the CER, where it's toroidally located. And so we have the option to shift our fits based off of this. So we can compute the bottom of the pedestal based off of a threshold and compare that to where the separatrix is in EFIT. And then we can do that in rho and in Z. And then we have a number of options. We can either form a constraint for EFIT, which essentially marks these spots in RZ space and says if we were to run a kinetic EFIT based off of these profiles, we could tell it to force the edge of the EFIT to go through that RZ spot. That's the most rigorous option for self-consistency. However, if we're not rerunning our EFIT, we can shift our diagnostic, essentially say that we're going to pretend like the Thomson is shifted in Z to align it with where the EFIT says the pedestal is.
Putting the constraint on the EFIT isn't more consistent if the Thomson is from a different 3D slice. Then you're going to give it data that disagrees with the magnetic probes at their toroidal location.
Which is actually what's happening.
Yeah. If you took one slice of a accelerator and put its constraints in a different slice where the shape is totally different, it would just be nonsense.
Yeah, if there's like I said, if there's a 3D effect.
And there is, because the F coil closest to Thomson is the most out of ground and the most off center out of all of them.
Right.
So Thomson always gets a larger error field than average.
Right, which is why we have the option to shift the diagnostic.
Which is the
So you're shifting the Thomson.
So we have an EFIT, and we're going to keep the EFIT where it is, and then we're going to say the Thomson is actually shifted in Z according to the difference between this red dot over here and this black line, which is the EFIT.
As opposed to 14 the boundary.
Right.
That seems to be the less famous, given it's what you said. The worst error is President Thomson.
And then the final option is to stretch the fit itself, which basically just kind of accordions the fit so that the red line or the red dot lines up with the pencil here.
So, and maybe one way to explain those options is that in the first case we're changing the equilibrium, right? So we have to do the mapping again, we have to do the slicing again, and we have to do the fit again. The second option, if you click, shifts the diagnostic. So we're keeping our equilibrium. So what we need to do is to slice and fit.
No, we need to remap.
Remap, no, well.
It's a new Z. So
that's done on the slice. So we only need to fit again. And instead, the last one, we're stretching the fit. And so effectively, we're done, you know.
The last one will just be to numerical precision. It's just modifying the fit. So yeah, there's nothing else to do.
Correct.
So that's the fastest.
Does it also modify your data so you can still compare them to the fit?
I don't.
No.
It modifies the slice data. It doesn't modify the raw data.
But then you can still overlay the slice on
Correct.
the fit.
Yeah.
Okay.
Right. So.
Oh, I can read it there. All right.
Yep.
Using the skill of reading.
And then if we recompute this, you'll see that they all perfectly go through the separatrix at the value that we wanted to peg there.
But shouldn't you pick different TE values for the slices that look like they're probably an element?
Yes, you probably shouldn't do this to the L mode slices at all. And so, you know, we might have wanted to do something different.
I think it's
When are we
okay.
gonna get
But this
the
was
other
just
Thompson?
for demonstration.
When are
So,
we gonna get the other Thompson? Another Thompson.
Who's gonna?
so I can reset it to the original mapping and refit it, for example, if I want to go back. Right.
I think it restored everything already.
No, it'll be shifted. See,
Yeah,
it's
yeah.
shifted off the.
Mhm.
So that's essentially what I had done here, where we argued that the Thompson was misaligned with the equilibrium, and so we moved to the foot of the pedestal.
Wait, which one was moved?
The fit.
The fit. So I'm going to refit. Okay. And any. Okay. All right. So we had similar workflows for the CER, which is a midplane measurement. So it gets shifted in R instead of Z. Or it can constrain a future EFIT, or it can get accordioned. Okay, so this can be done separately for the density and the based off of the density pedestal, or based off of the omega E zero crossing at the edge. Two different ways of identifying how the CER channels align with the supposed separatrix from the EFIT.
Now CR is not next to a misshapen F quote the way Thompson is. So the most likely reason for the misalignment might be an RMP that you're applying.
Right. Yeah.
But isn't it near a node in the n equals 3?
I would have to look at that. I don't actually know where it's located. Okay, so once we're happy with that, and I should say that the density alignment here is a little bit more involved. It's based off of the fit of the ion density as well as the electron density, and aligns their correlation. And so you have NE here based off of our fits and ion density here, and it's trying to correlate them and line up the two pedestals. And so it's calculating the red spots here versus the vertical lines where the EFIT thinks the edge of the plasma.
So it's based on the assumption that the carbon concentration doesn't change
That's right.
in the edge.
And then the omega E is a very good physics argument as well. That should go through zero at the edge.
Well, what that alignment does, it tries to align the region of maximum gradient. So basically, if you have a pedestal in the electron density, it tries to align pedestal in the carbon density so that they match. And the result of doing that, so when you have a slight misalignment between the two profiles, what happens is that your Z effective can go haywire pretty easily. And so by aligning the region, you know, how the two profiles kind of grow together, you know, how the gradients grow, usually you get a reasonable, you know, a well-behaved Z effective. So that's kind of a, you know, I don't know, maybe a minimum of energy argument.
Should you move the CER or should you move the Thompson based on this?
So usually what we do is we set the Thompson based on the temperature at the foot of the pedestal, and then you move the CR to match the region of maximum gradient.
But you're not recalculating the temperature at the foot of the pedestal based on any power balance arguments. You're taking kind of an average or typical configuration.
Correct.
Which can vary from 50 to 150 according to table 13 of Stingman's 2015. So maybe you know more about the CER pedestal than the Thompson one even after applying the shift based on TD.
Maybe.
If you have omega E, you could say that that's your fundamental constraint, shift CER based off of that, and then shift Thompson to match that, for example.
That could
Is
be.
there a way to do that?
No, not yet.
No.
But that's a good
But if
brainstorming session
anyone
right now.
has a use case for that, then we can add it to the dropdown for Thompson.
If you shift the CER ion densities, shouldn't you also shift the CER rotations by the same amount?
Right.
Yeah,
so,
the whole CER diagnostic system, all the Z points, or sorry, all the R points will get a delta,
Okay.
and it'll remap to rho.
right. It's not only the temperature is only or temperature or density is only the measurement that you use to make to calculate by how much to shift. But then all of the measurements that are measured by that diagnostic are shifted in the same way.
That's right. Okay, so these are options, and they're very powerful, and they can also, they should be treated with respect.
There's one that says 0.91.
Right.
If your
Right,
CER
this is,
profile's off
so
by 9%,
if you see this, so this is a good point. When you click the compute, it computes the values and it gives you the values here. And you can say, I don't believe this L mode one, these points in L mode here, I don't think they should shift at all, because I don't believe that there's pedestals that I can correlate. And so you can set those to be 1.
I feel much better right now.
Great. So, so try to think it through, and this still does rely on physicist interaction.
Does the 0.96899 seem physically plausible to you?
I think we should move on.
Yeah.
Sorry.
It's okay. I think these are good physics questions, but they change shot to shot, timesless to timesless, and I think.
Yeah, this is probably still during the L
10%
mode.
error in your CR alignment is a red flag in any shot, in any case.
Let's see. Oh, that's not going to do it. Yeah, we just need to look at that slices in H mode or L mode, see if it's even a valid calculation. Okay, so now that we have this, actually, any step along the way, we could have come to this plot tab, which has a huge array of plotting options to visualize the profiles that we've been making. And so you can select raw diagnostics to plot, the fits. This will plot all the fits, but we could select, for example, all the electron quantities. We can plot a static time series with a couple of row to see the time evolution, different rows. We can plot 1D profiles. Interactive would be similar to what we've seen so far. We can plot them all together to see how the thing evolves. And we can click on different points to see where they came from. It's nice and interactive. And then finally, we can see 2D profiles, either static or interactive. The interactive ones are pretty cool. You can click around and the 1D profiles will change. Okay, so what are we at? We're at 50 minutes. At this point, I could take questions, or I could go through 2D fitting, but it seems like time's pretty much up.
I think we can go to 10-15 minutes extra without an issue.
The silly presentation started too.
Well, some of us can leave, not everybody.
Okay, then let me ask a question first. How does the profile shifting work when you do 2D fits?
It's not enabled.
So, sorry, in the interest of time, can you talk about the export and then show the 2D workflow?
Yeah. Okay, so now that we have these fits, they are right now as something called a data set, which is essentially an in-memory representation of a netcdf file. if we hit P, it prints. You can see it knows meta information about the dimensions of each quantity, which things are data and which things are coordinates, and then it has some attributes. And so this would save itself as a netcdf, which many programming languages can read quite easily. However, there are industry standards for other types of profile output. One of these is, for example, the P file, which is an ASCII format for profiles, and we can convert our derived quantities into that form. If we generate these P files, they live here in the outputs, and then we can export them to, for instance, anywhere on the local machine or a remote machine. And so this is nice for handing off profiles to people who are working outside of OMFIT. We also have the ability to compare to GA profiles or Osborne profiles if you've done profiles for this shot using either of those tools. This will bring up a plotting interface to compare those plots side by side, or overlaid rather. All right. That cover everything?
For the 2D, do you think we can get a quick run through with a
Quick run through for the 2D. All right. Let's do it. So I'm gonna just import fresh.
Since we don't have a tutorial for the 2D, this is a good reference for pointing
Okay,
people
so this is an under construction alternate workflow for 2D fits, where we fetch the raw data, map it into space, and then we don't bother slicing in time before fitting in space, but rather we do a 2D time and space processing of the data. Okay, so all the fetching and selecting is all the same, so I'm just going to run those two steps all together here. And this is kind of the power of this main tab. If you know already that you just need to repeat something. See, the outputs will be the same. Then I'll update the GUI. So this is going to be not a fitting procedure so much as a processing of the data. Basically, what's going to happen is it's going to take dense, unstructured data in row and time and interpolate it to a very dense, regularly spaced grid, and then do Gaussian image processing on that with a couple tricks to keep features such as pedestals and sharp time evolutions. Okay, so where are we? So yeah, all this is the same. We might turn on ecolloidal, for instance. Oh, I know what happened. Okay, so we can move to fit, go to TE, our favorites, and there's a reduced number of options here. Basically, we're going to specify sigma for the spatial dimension that we care about and a time dimension that we care about for the smoothing. We can do outlier rejection, which will basically do the fit once and then reject outlier points. This can save us some time on channel selection, because if there's an obviously terrible channel, it will get automatically removed via this. And we can do Monte Carlo sampling to get error bar uncertainty quantification. So you can compare the speed here. It's quite fast, and it shows us the linearly interpolated data, each data point here, and then the fit with nice smooth contours evolving in space and time. And then also a estimate of kind of the quality of the fits. And you can see that maybe we struggle to get the exact top of the, or this is actually at row 1, so just the bottom of the pedestal here. That's probably because the values are just very low, or the normalization on this is pumping up those values, but fit looks quite good in general. So you can also see here a more typical plot where we show a cloud of points within a time range, and then the fit going through it, kind of similar to what you might see in other tools that didn't do the time convolution. You can see that there was a point way down here. It didn't really influence the fit. It was probably rejected due to our outlier rejection. Yeah, so then if you go to the plot, you can plot raw data and the fits. You could actually do this in the other method as well. Oops, there we go. Oh, here we go. So we did return the derivative of this fit, and this is way too many times, but we could select it. Here, 2800, and we only want TE. So you can see a cloud of points and the fit going through it. So that's super fast. You do fit all, it'll do them in parallel. And so you can get, this is especially helpful if instead of 10 times, we wanted the profiles smoothly evolving over 300 time slices, for example. In which case, you would spend all day going through each individual slice to check if it's okay, hunting out the poor chi-squared bits and adjusting parameters. Questions on the 2D?
So, and I guess that this will generate, if we look in the OMFIT 3, this will generate under fits the how many whoever time slices we requested, right?
That's right. So this is still just 240 by 11, but we could do many more time slices and bits. You can see here, it was just as fast, but we got 300 time slices.
So if you hit return on that T in the, yeah. So that's the, those are the profiles fit. Very
Right.
nice, very nice.
That's the power of the 2D fit.
Good, so you managed to do it everything in 1 hour.
Perfect.
2 minutes to go.
Yeah. Maybe do you want to show the documentation where people can get this?
Oh yeah, so I forgot to mention, that was definitely something I wanted to do. So when you go to the fit methods, it can be overwhelming when you're doing the 1D process to figure out which fit method is correct for your particular profile. Each of them has its own strength for different physical situations. There's a link here to the web, to the documentation. That will take you directly to an appendix that goes through each of these fitting methods and tells you what it's good for, what its strengths are, what its weaknesses are, etc. So you can choose the best one. And this tutorial goes through a full example for D3D using this shot, in fact. Has a lot of details, and it's also available on the OMFIT sites, which OMFIT would get you. Right, modules, and then go down to profiles. You can see a description as well as a link to the Google Doc tutorial and some good presentations. And many people have contributed, so thank them all for their time. And cite the appropriate papers.
Yeah. Good. Anyone has questions locally or maybe remotely?
Yeah, I had a question about outlier rejection. I guess in the 1D fitting, it doesn't appear to be any outlier rejection. Is that true?
Yeah, so the evolution of this is that in the 1D fitting, we focused on this select interface where you would, check the data in time and check the just raw unfit profiles and kind of identify poor channels this way. But there's nothing that says we could not add an option to just reject outliers.
Well, one thing that is that the 2D fitting, I think, takes really advantage of the neighbors, right? So, if it's only one channel that goes bad for, a couple of time slices, you can use the information around you to kind of, not fall in the trap. And instead, if you have a single time slices, I think you're much more susceptible to outliers.
Yeah, so the issue here is that this channel that we turned off actually wasn't bad every time, right? It was reasonable all the other times. And so as you were fitting single time slices, this one time slice would have come down here, and then probably the fit probably would have been able to come up somewhere near that before dropping back down. And so it wouldn't actually be recognized as an outlier. But then if you do it in 2D, the fit's going to stay down here because it can see all the other data down here. And so it will be recognized as an outlier.
Yes, so there are algorithms that you can use in 1D to get rid of outliers automatically, and I think that would be very useful. But I can talk to you about that afterwards.
Yeah, that would be incredibly useful, and we'd love to incorporate it if
Yeah, or maybe even use the 2D fit to precondition a 1D just to do the outlier, and then I think there are options.
That's the other thing is the 2D fits are quite fast, whereas the 1D fits, if you're using Gaussian profiles or Gaussian processing, it can take a little while per time slice. And so iteratively doing it can be expensive. But if you have a quick way of doing it, then that'd be great.
Yeah, it was in 1992 we did this for TFDR, and we had an algorithm that was you would do multiple refinements and then get rid of the outliers that way, and it was very reliable, like 97% reliable.
Yeah, that'd be nice. That'd be very nice.
So I mean, it was 1992, so it was fast then. So
I mean,
which makes
ultimately this module is drawing lines through points, which I think was solved many ways over time quite successfully in many different situations. But the fun of it is that the plasma always gives us new situations, and so the power of this is that it has a lot of options.
Well, and also I think the power is that it's very modular. So adding a new feature, adding a new fitting method, adding outlier rejection,
right?
Script. I think that it makes it pretty easy without having to change everything.
Yeah, we're always trying to incorporate the best practices from different machines. So the pedestal alignment feature is something that D3D was doing, and it now is available on other machines that might also have similar 3D effects, for example. So.
Okay, so if there are no